situation. You're dealing with a large team and you have to build the infrastructure as well as the cost that goes towards demonstrating and developing the technology as well. So what it really comes down to is how much capital investment there is over a long period of time. In many of the examples that I've given you here, robotics, the field robotics that we've been working with is a much more of a strategic play. It takes many years to work with. So you need the investment partners, whoever they might be, or the industry partner to want to take out that long period of time. That's really what it comes down to. If you, the case where we tried it, what happened was that we kind of went out there, start to build the robots and start to demonstrate and commercially demonstrate everything was okay. But to then scale, to go from 10 robots to 100 robots, needs a certain type of manufacturing capability and investment to kind of get that. And in Australia, that wasn't available. Maybe somewhere else in the world, and as we know, we can kind of see everything from drones and what happens there. You can start to manufacture, reduce the cost and that makes better. So it's really around capital investment and duration.
Okay, there's a question in the middle, far back, yeah.
Hey, Salah. Oh, whoa, that's sensitive. Hey, Salah, thanks for a really inspirational and great talk. This is sort of a follow-on to the previous question, which was, you've been very open about how incredibly difficult this journey over 30 years was. Thinking ahead to the next 30 years of robotics innovation, what things could the research field or government or even in terms of public expectation do to make this whole journey easier?
Oh, wow, okay. Good question. I think it's getting a bit easier now to develop the technology and demonstrate the technology because of the manufacturing scale that's happening at the moment now. I personally, in my lab, the fundamental thing is as soon as researchers start, PhD students start and so forth, the thing that it's baptism by fire. They get thrown in the water. We have to, and they have to swim. It's one of those things where getting into the field becomes really important. So I think from internally, getting them into the field and learning about what works and what doesn't work and how that structures their research is important. Within the university, being able to kind of develop I think talent pool is an important part. So being able to try and identify talent pool from undergraduates all the way through. Finding the right industry partners is important. The learnings that I've had are finding the right champion inside the industry partner, someone who's willing to kind of stand up in front of the managers, build the business case, etc. You need that person inside the industry partner that will help you go through. We've lived longer than many CEOs and many of the industry partners that we work through, so you have to go through that process of constantly re-engaging, and that becomes an important element. From a government perspective, I'll be honest with you, the only time the university's ever been interested in our work is when they've had to write an impact statement for the government. And then they come along and think, oh, there's engineers somewhere on the other side of the campus, let's roll them out and let's write something about it. So I think there's still a bit of a challenge there. I think, and especially in the Australian context, as you know, and geopolitics, I think there's still a bit of a challenge there to kind of get government on side in that way.
Okay, I think we take last two questions, one over there, one here.
Okay.
So
I'm here.
On the right.
In
yeah,
front.
on the right, yeah,
Okay.
please. Yeah, all right.
No, thank you for your inspiring talk. I have like hundreds of questions to learn more about your very inspiring work. But I'd like to know, like you mentioned like several applications, and for each application have partners. And these partners are a very important part because they give you some feedback or give you the problem. But from the side of these guys, like robotics is kind of tool, like they need that to working, doing the job, or I don't know. How can you share with us some idea, how can you keep this guy involved during this development part? Because like they are not seeing the end, they are just seeing the development,
Yep.
And how can you get this guy engaged? How did you do that?
Yeah, again, a good question in terms of that interaction piece and what that means. So I guess one of the key things is fundamentally, it was never about what was the favorite research topic and how can I push that out. From my personal perspective, I always saw myself as an engineer, and there was a problem there, and I thought, okay, how do we solve that problem? So when you engage that way, the first thing that happens is they kind of see that you're trying to solve their problem. Okay, and their problem can mean, well, you know what, for the last 2 PhD students that I've got now, they're working on optimization. Now I'm going to look at machine learning for whatever it is. So it becomes that process of engaging with them and feeling like you're going to work for them on their problem. Then the other part is, you know, we had to, our programs were never like, come back in 3 years and we will show you what we did. It was always about every month. We have meetings now every week with our industry partners on the project. This is what the progress is. Every month there's a broader industry engagement piece with that particular industry partner. Every quarter there's a workshop that kind of ticks off where we are with what they think is the right things that we have to go through, and allowing the project to modify as you go through. And that's a bit hard because you want to push the research out, you want to do some really good novel research, and at the same time you want to make sure that the industry partner's happy. The industry partner wants you to kind of constrain that research as much as possible. So it's a bit of a tango, and it's a bit of that process of working with them. But I think getting them on side, knowing that you're trying to solve their problem in the most innovative way, because at the end of the day, they came to you because they want something novel. It's competitive advantage, or they want something more efficient or whatever. So engaging in that process was what I found was probably the way that you keep them engaged. And being honest with them, I think at the end of the day, you know where the research is, you know how robust it is, you know what will work, and you have to be open with the process about what could fail and what might not work. But you shouldn't, in my experience, never say that I will deliver something in the next 6 months. You're always constantly working with them and showing them progress and updates as you're going through.
Okay, we have last question. Is that a question over there? No, okay. A question here, okay, yeah.
Hi, thank you, Professor, for your wonderful talk. So I noticed you mentioned like you looked at the PRM RIT star from way back, and it's only going to be started to deploy next year. Do you think that horizon is shortening, where like the latest breakthroughs are going to be deployed faster in field robotics in the next maybe 5 years? And what do you think is the most, like a guess of the most promising new latest ideas that you think will be useful for field robotics?
Okay, is it getting shorter? I think it depends on the industry context as well. You know, we've seen, like, for example, over the last 2, 3, 4, 5 years, and we're just talking about it during the break, humanoid robotics, right? So, and it's going to happen the same thing with drones. So they end up getting cheaper, they end up becoming more ubiquitous. You can put them into your lab. You can start to kind of demonstrate, you know, your favorite algorithms on those systems. The key thing that I wanted to say here was, is the humanoid robot, for example, or the drone, and I'm not trying to pick anything, or manipulator, or whatever it might be, or field robot that we're looking at, is that useful to the end user? So that's the kind of goal. That becomes the part that we want to kind of focus on. So in terms of deployment and time, different industries work in different ways. If you're thinking about commercial airline, actually it got deployed into their systems around 2018. But it takes that long for internal business processes to change, for people to understand how to operate it in their context. Then it took just as long to convince commercial aircraft operators to say, okay, we will build an aircraft specifically for this purpose. And then it took also some time for the air traffic control people to believe that their system, this new system now, will be safe and operable. So that's the reason why in that particular context it takes some time. In the agriculture domain, we went from out of the lab into a spin-out and demonstrating that you could be commercially successful within 2 years, and that process. So different industries will have different timelines, I guess, and it really comes down to their operating processes. On that second question about, if I could answer it at the end of this week after I've seen some of these talks, I'll answer it for you then. But look, I think there's various elements there. I think soft material, new materials that are coming out, quantum computing that I think would be an interesting element. I know this all sounds kind of, but if you told me 10, 20 years and what we would start to do now to kind of look at that, I think that has a certain element to it, and we're kind of exploring those with new materials, deformable large field robots as an example, as well as new computing techniques. I think they're the kind of areas that we're looking at. And some of the things that we're learning about, you know, VLM and LLMs now and whatever might be in that interaction space where an operator, so for example, a first responder, a fire person who doesn't know anything technically about the robot, can actually interact with something like that in a very serious situation. Is probably going to be one of those other areas that I think will over the next few years.
Okay, let's thank Salah again for the nice keynote.
Thank you.
So next session is humanoid. All right. Hello, everyone. Since we're 10 minutes, around 10 minutes behind, we'll probably start the next session anywhere between 7 to 8 minutes late. Welcome to the Humanoids session. My name is Dan Fei. I'm assistant professor at Georgia Tech. This is Xingxing, my co-chair. Do you want to introduce yourself?
It's okay. My name is Xingxing Zuo. I'm from MBZUAI. Yeah, please.
Okay. So we have 13 papers. One of them papers, unfortunately, do not have a presenter. So let's start with the first paper. Husky Humanoid Skateboarding System via Physics-Aware Whole Body Control, presented by Jingrui Han.
Hi, everyone. It's a great honor to be here to kick off the Humanoid session. I'm Jingrui from the University of Hong Kong and a research intern at TeleAI, co-advised by Professor Luo Ping and Dr. Chen Jiabai. Okay, so today I will present Husky, a learning-based framework for humanoid skateboarding, a very challenging and unexplored task. So let me introduce how we achieve this. Inspired by real-world skateboarding, we first analyzed the humanoid skateboard system and derived the equality constraint between the board tilt angle and the truck steer angle. And this captures the key lean-to-steer behavior. Body leaning steers skateboard turning. In other simplified models, the skateboard cannot actually turn. In contrast, our model embeds this equality constraint into simulation and preserves this key lean-to-steer behavior. Next, we design learning strategy across different phases. In the pushing phase, the objective is to follow a desired forward velocity, and we adopt the MP framework to encourage more natural and robust pushing behaviors. So as shown in the video, the humanoid can push the skateboards at different speeds, showing human-like motion patterns. For the steering phase, the objective is to regulate the board towards a heading target. Using the derived equality constraint, we introduce a kinetics-guided tilt reference. And showing in the video, the red dot is the heading target, and the humanoid can regulate the board smoothly towards it. However, directly transitions between pushing and steering are very difficult since they involve different learning objectives. So we introduced a trajectory planning-based strategy to generate intermediate reference motions. This allows the humanoid to follow these reference motions and achieve smooth and coordinate whole body motions. And they can seamlessly switching between pushing and steering. Overall, our training pipeline is built on the Mojo Collab framework, enabling the humanoid performing stable, continuous, and expressive humanoid skateboarding. And you can command the humanoid reach any velocity and any heading target. We successfully deploy our policy in the real world. To our best knowledge, this is the first time that the humanoid use a learning-based policy to complete continuous humanoid skateboarding cycles. And thanks to the domain randomization strategies, our humanoid can also handle indoor skateboarding with different heading targets. And take a closer look to the transitions. After mounting on board, the humanoid finishes the reorientation procedure. And our pipeline adopts to more skateboards with appropriate skateboard system identifications. And here are more clips about the outdoor experiments. And to be honest, the seam to real gap still exists. And you can see he's pretty struggling here. And from the mirror reflections, you can see that we are constantly holding a protection pad there for some emergencies. Yeah, and more surprisingly, we found that our policy shows great potential during the zero-shot evaluations on some unseen terrains, such as slopes and stairs. So we open sourced our training pipeline and assets and hope our community can build on them for more interesting and challenging tasks. And the last thing is I'm required to make a quick AD for my mentor, and we are ready to launch a startup in Shanghai, China, focusing on humanoid whole body and local manipulation. And whether you are interested in my paper or our business, feel free to chat with me in our poster sessions. So that's all for my presentation. Thank you.
Next paper is going to be Perceptive Humanoid Parkour, Chaining Dynamic Human Skills via Motion Matching, presented by Jen Wu.
Yes, you can start. Okay. So Hi everyone, I'm Zhen from Amazon FAR. Today I will present perceptive humanoid parkour. The goal of this project is to enable humanoid robots to autonomously perform long horizon parkour using onboard perception. So first, where are we today? Recent work has shown that humanoids can perform highly dynamic skills such as flipping or climbing onto obstacles. However, these systems are still fundamentally motion tracking, which means even an environment change, the motion will not. So if here we move the table away, the robot will still try to execute the same climbing motion at the same place, and of course, will fail. So while motion tracking enables dynamic skills, it does not yet enable autonomous behavior. And our goal is to bridge this gap and learn our perceptive parkour policy. Given perception, depth observations, and a velocity command, the robot autonomously traverses complex environments, as you can see here. So what's the challenge here? The challenge is actually not teach the robot how to climb. We know motion tracking can already do that. The real challenge is teaching a robot when to climb. So if the robot starts far away from the obstacle, it should keep walking first. If another obstacle appears after the climb, it should smoothly transit to the next skill. So in other words, we don't just need isolated skills. We want autonomous long horizon behaviors. And interestingly, the video game industry has been solving this problem for years. So in games such as Assassin's Creed, characters seamlessly compose locomotion and parkour skills into coherent behaviors. And although these systems are not physical, you can see they are very effective at solving this behavioral conversation problem. The key technique behind is motion matching, and we borrow the same idea for data generation. So starting from a skill library containing locomotion and atomic parkour skills, motion matching composes them into long horizon parkour behaviors. And by randomizing the approach conditions and obstacle configurations, we can generate a diverse data set of parkour behaviors. As you can see here, the robot can approach the obstacle from different locations or using different skills. We'll still have a very natural and smooth transition. And now we have a long horizon parkour trajectories. We then use a teacher-student learning framework to learn our perceptive policy. So first, teacher policies are trained to track the trajectories using privileged information, and are then distilled into a depth-based student. And the greatest thing is that because the generated trajectories cover a diverse approach conditions, the student learns how to execute the same skill from many different starting configurations, rather than just following a single script behaviors. And the resulting policy can zero-shot sim to real. So here we show the robot can perform many parkour tasks in the real world. Here it performs a vaulting and climbing onto an obstacle which has the same height as the robot itself. And jump down and rolling. And this is another kind of vaulting. And all those behaviors are generated from only onboard perception and a simple velocity command. So no reference motion is needed during test time. And that means the policy is not tied to a specific parkour course. So here we actually enter into a course and modify it, and the policy automatically adapts to a new configuration and continues traversing. So to summarize, motion tracking gives us dynamic skills. Motion matching turns them into long horizon behaviors. Teacher-student learning turns these behaviors into a perceptive policy. Together, they enable autonomous humanoid parkour. Thank you.
Next, we have Size Zero, an open foundation model towards universal humanoid local manipulation, presented by Hongyi Jing. Please start.
Hi, everyone. I'm Hongyi from USC, and today I'll present Size Zero, an open foundation model towards humanoid local manipulation. So today's humanoids can work in balance really well, but manipulation, especially local manipulation, is still far from solved. So this is exactly what Size Zero targets, a foundation VOA model for humanoid local manipulation. So in general, Size Zero is designed as a triple system architecture. It's built around multiple training stages. Each serves a different purpose and uses a different action representation. So first of all, we have a system 2, which is a VLM backbone here. So in stage 1, we pre-trained the VLM backbone on 829 hours of EagleDex human egocentric videos. And the action here is a 48-dimensional end-effector pose, and we compress them into around 13 discrete tokens with a fast tokenizer. And this VLM understands the scene and produces high-level intent as end-effector poses learned from human videos. And then we have system 1, a flow-based MMDIT action expert. So in this stage, we freeze the VLM and use 30 hours of real humanoid everyday data to train the multimodal DIT action expert that predicts future whole-body action chunks, transferring VLM priors onto continuous joint actions. So we use multimodal DIT head here since it concatenates VO and action features from the beginning and lets them fix more effectively. And finally, we have System 0, a RL policy for lower body control. So System 0 here is a high-frequency decoupled RL pipeline. So the high-level policy predicts arm and hand joints directly, plus torso pose and velocity that System 0 turns into lower body joints. And the same policy drives our VR-based teleoperation for data collection. So together, these three systems separate reasoning, action generation, and control, forming a more scalable and effective architecture for humanoid local manipulation. So in our learning pipelines, first, we pre-train the VLM on human videos, enabling the model to learn task semantics and human behavior priors. And next, we freeze the backbone and train the action expert on real humanoid data, grounding those representations in whole body control. And finally, we fine-tune the model using a small amount of in-domain teleoperation data and enabling rapid adaptation to long horizon tasks. So together, this recipe tells a clear story. That is, scaling the right data at the right stage is the key to building capable humanoid intelligence. And lastly, we applied RTC during deployment. On the server, VOA inference runs on an 5090 GPU within a synchronized control loop and inference loop. The control loop maintains the currently committed action chunk and the robot state, while the inference loop predicts the next chunk conditioned on the actions already being executed. And this is the key idea behind real-time chunking, or RTC. So you can see in this video, without RTC, with over 2.5 billion parameters, a naive rollout could introduce latency and a stop-and-think behavior that is unacceptable for reactive control. However, with this customized RTC deployment pipeline, Site0 could produce really smooth, stable, and human-like behavior in the real world. So finally, we evaluate Site0 on 8 real-world local manipulation tasks. It achieves the highest success rate across all tasks and subscales using only 10% of pre-training data, which shows the importance of scaling the right data in the right way. And the evaluation also confirmed that every one of our design choice contributes to the final performance. And you can also check more demos on our website. And thank you guys for listening.
Okay, next we have Ex Loco towards generalist humanoid locomotion control via synergetic policy distillation, presented by Jingrui Han.
So hi everyone, it's me again. And on behalf of my friend Dewey, I'm excited to present the paper Ex Loco. And achieving a unified generalist policy remains an open problem in humanoid locomotion. To bridge this gap, we synergize specialists in locomotion for recovery and whole body coordination into a single generalist controller, as the simulation shown here. And our pipeline begins by training 3 specialists, each optimized by the best performance in locomotion for recovery and whole body motion tracking. And to integrate these skills, the case-adaptive specialist selection mechanism chooses the right specialists based on the robot states and the surrounding terrains. And the specialist annealing rollout and forward injection mechanisms are introduced to facilitate the learning of the specialist knowledge and the policy's recovery resilience. And as shown here, the vision-based generalist policy shows robust navigation across diverse terrains. Leveraging depth information, the policy adaptively chooses the right behavior response to the environment. Ex Loco also shows great robustness in fallen recovery, enabling the robot to get up from any fallen states. So when forced into a fall by external forces, the humanoid can automatically regain his footing and continues the locomotion task. And this is further validated in this long clip. And the humanoid is trying to traverse a set of complex terrains, and X-Local can achieve high success rates in the simulation without any reference motions. We successfully deploy our framework in Unity-driven humanoid robots, and using the onboard vision, the robot automatically executes right behaviors to traverse complex real-world environments without any reference motions. Specifically, the policy runs at 50 Hz and driving solely bound velocity commands. To bridge the depth image sim-to-real gap, we inject Gaussian noise and burn into the depth images. And we also randomize the camera parameters, including positions, orientations, and FOVs. So on the real robot, hole filling and Gaussian filtering are also applied to the real depth images. And we can see from here, humanoid can execute a lot of locomotion tasks. So in this long clip, the X-Local integrates a broad range of motor skills, such as climbing up the box, and initialized by fallen states, it can gaze up and climbs up and down the stairs. Yeah, it's struggling. And lowering his body and to roll under the hanging bar and finally continue locomotion task. All within one single policy. And during the robust evaluations, we found that the policy can resist the external forces and gaze up. And even in some near failure scenarios, the humanoid can stick up to it and finally finish the task. So that's all for X-Local, a general motion controller for humanoid locomotion. We believe it's a good example for the low-level controller for future humanoid local manipulations. Thank you. That's my presentation.
Okay. Next, we have learning to evolve, multimodal interactive fields for robust humanoid navigation in dynamic environments.
Okay, thank you, everybody. And today I will introduce my paper named Learning to Evolve Multimodal Interactive Fields for Robust Humanoid Navigation in Dynamic Environments from Peking University, Oxford, and ETH. Don't mislead by the title that the learning here is not the learning from the VRM or RL, but the final goal of our work is to learn from the interaction with the environment. And that is to say, and I think it freeze. Is this video freeze? Yeah? Sorry? It didn't change. The next one.
It's changing.
Okay, sorry. And the main goal of our, you can see that from human beings used to learn from the past, and when it observes the current, it will know what changes. And it will also have the capability to learn from now and to predict about the future. And now the explicit representation for robotics could already achieve to learn the spatial changes from the past to the present. And our work is to use a multimodal interactive field to learn this process. That is to say, we introduce 3 different fields. The first one is the appearance field. That, like human beings, this field learns from the CDGS semantic heat map. And then we extract the spatial information into a scene graph. And then we also learn the geometry from this information. But in humanoids, there are 2 main challenges. The first one is the camera jitter, which introduce motion blur. And the second one is the dynamic changes of our environment. And the goal of our work is we want to make our work from a passive map user to an active knowledge evolver. And the first one is the appearance field. We distill some high dimension semantic information into the 3DGS, as well as we introduce a confidence for robustness to quantify the uncertainty. And you can see from here, this is the render result for our work, and it's much more high fidelity, just like human beings when we recall some things. And we extract from these render views to extract the high-level information, like the spectral field, the spectral relationship in the tree structure. And the edges are the spectral information, and the nodes are the semantic information of each object. And that is what we call the spatial field. And we use this field to evaluate our robot by these four ways. The first one is the detection. When the robot detects a speck in the discrepancy, it will actively scan the environment and update the map in a from top to bottom manner. And then it will reply to the correct place. And we also update from a top to bottom manner. That is to say, we did not want to update the 3D Gaussian. We first update the semantic information in the scene graph, and then we update the local 3D Gaussians to make the appearance field much better. And we also use the feed-forward transformers to guide the geometry, because the 3D Gaussians they are sparse as well as the point cloud. And now we use the feed-forward to get the watertight meshes from the observations. So we can use these observations, we can use these 3D meshes to do manipulation, to choose the most safety pose to navigate. Instead of just walk near the object, we want to pick up a pose that is perfect for manipulation. And that is what we want to do. And we introduce an IPS factor for this process. And you can see from here, a tiny movement of this sofa will cause some static pipeline to fail. But in our work, we could use the interaction between different fields to make our success rate in dynamic scenarios much higher than others. And nowadays, we are now in the stage of the first law of Newton's motion. That is to say, we can use the explicit representation to know about the past and the current. But with the introduction of the world model, we could learn more about what is going to happen and to predict the acceleration or the effect of forces between the objects. And that is what we want to express, that you do not have to use RL or VRM to do the involvement for a robot. The interaction maybe can also help that if you are lack of GPUs or you are lack of resources. And that's all I want to say. Thank you very much.
All right, next we have Mobius, a multimodal bipedal robot that can walk, crawl, climb, and row, presented by Alexander Sperberg.
Okay, we present Mobius, a multimodal bipedal robot that can walk, climb, and roll. So most robots have a morphology that have limited traversal modes, at least out of the box. But in our case, we have a biped robot with a back rail, flat feet, and two-finger spine-based grippers. So this gives us a lot of different modes that I can do. So we have a mode selection, which can be from a user. It goes into primary mode, being either biped or quadruped, and then we have secondary modes, such as biped walking, pull-up, climbing, crawling, and rolling. And we have underlying planning and control schemes that can activate in one of these modes. So one of the interesting parts of this is a high-level multimodal planner, which is a MIQCP optimization, to try and get the robot to a goal state while also visiting as many cells as possible. And we also include some obstacle constraints, terrain constraints, but importantly also the mode constraints. For the pull-up motion that we'll see, we use a force controller. So we have FD sensor that measure wrench disturbance, and then that produces the corrective interaction. The arms produce the corrective interaction-driven velocity to counteract this disturbance and track a reference wrench. And then to guarantee safety, we use a reference governor to satisfy our force controller, which involves calculating the maximal output admissibility set, which simply defines the entire set of initial states and references for which the system can operate without safety violations. For locomotion, we use reinforcement learning with typical PPO algorithm that I'm sure all of us are very familiar with to do this type of locomotion. And then we do direct transfer to the real robot. So the videos from here on out is just to sort of validate the hardware and the different tasks that I mentioned before. So here we'll show all the different modes it can do. So it can go into quadruped, roll, and also stand back up. So in case it falls, it can stand and also use the back rails for recovery. For the force control in the pull-up, we show one method where we don't use the auto-tuner. So here the gains are not calibrated. So of course, the pull-up motion will be very unstable. And then here we have it with the auto-tuner. So now the controller is much more stable. And I will now demonstrate the compliance of the system by essentially pushing the robot down, and then the robot sort of comes back up again. It's essentially a spring damper system because we're tracking both a wrench and also a position. And we also demonstrate I can do repeated pull-ups. So this is just to validate on hardware that there's no human intervention. I can still do the pull-up. We use a simple visual server to kind of track the handlebars of the slide for the next demonstration video, which is to climb the slide and then roll down. So it aligns to the slide and then performs this motion. And then at the top of the slide, it's going to roll down. Now, as it rolls down, there's obviously no planner or controller. We just pray and hope nothing happens. 8 out of 10 times it succeeds, but those 2 times, it was very late nights fixing this robot. All right. Thank you for listening.
Next presentation will be telegate, whole-body humanoid teleoperation via gated expert selection with motion pair. The presenter will be Jie.
Hi everyone, I'm Jie from University of Science and Technology of China. Today I will present our work, telegate. It's a whole-body teleoperation framework for humanoid robots. Let me start with teleoperation. It's useful because it collects high-quality data for embodied AI. So we build a whole-body teleoperation system. Here you see the system doing manipulation tasks. But our system can do much more than grasping. It can jump, kick a ball, walk, and get up from the ground. So the motion range is very wide. Now let me explain why this is hard. The first challenge, we can't see the future. Offline tracking sees the whole future motion, so the policy can prepare early. But real-time teleoperation is different. The policy does not know the next move. So the dynamic motions like jumping and get up get much harder. The second challenge, human motions are too diverse and very different from each other. When we add more motions, it becomes average everywhere and good at nothing. So how do people solve this today? A common way is distillation. They first train many experts, then they distill them into one general policy. But distillation is lossy, so the general policy falls below the experts, especially on dynamic motions. This leads to our key question. Can we design one controller that matches or even beats every expert? Our answer is delegate. It has 3 stages. Stage 1 is data collection. We use an inertial motion capture suite to collect about 2.5 hours of data, then split it into 4 expert groups by dynamic similarity. Stage 2 trains each expert with a motion prior. Remember, we can't see the future, so we use a VAE. The encoder reads the past, and the decoder predicts the future. This forces the lantern code to contain the next move. We train it together with a policy, which solves the first challenge. And stage 3 trains the gating network. We freeze all experts and only train a small gate. At every step, it picks the single best expert. So the problem changes from dual motions to pick which expert. This solves the second challenge. Let's look at the simulation. On the left is distillation. On the right is our gating. You can see distillation gets worse and fails, while gating stays expert level and succeeds. Now the numbers. Our gating reaches the expert upper bound and sometimes even beats it. It's because the It picks the best expert frame by frame. Compared with other methods, Telegator is the best overall. Finally, the real robot. We deploy Telegator on a real robot. This validates sim-to-real transfer, and one single controller handles many motions. And I wanted to emphasize one point. We use only 2.5 hours of data. Other methods usually need much more than this. To summarize, Telegator is a unified teleoperation framework. Gating keeps every expert complete and the VAE prior as anticipation, always only 2.5 hours of data, which we have open sourced. You can find our paper, website, and video in these QR codes. Thank you.
The next presentation will be generalizing from references using a multitask reference and goal-driven RL framework. The presenter will be Margaret.
Sorry, this is very bright. Hi, everyone. Today I'll be presenting our paper titled Generalizing from References using a multitask reference and goal-driven RL framework. In this paper, we essentially demonstrate how to combine imitation and goal-driven reinforcement learning to obtain natural, robust, and generalizable behaviors for humanoids. So our motivation behind this is as follows. Imitation can produce natural and coordinated motion. However, it's brittle outside demonstration distribution, and is coupled to reference timing. On the other hand, while pure test-driven RL can produce adaptive behaviors, it often results in unnatural or aggressive motion and requires heavy reward shaping. So in order to take advantage of both of these methods while mitigating their cons, the key idea behind our framework is to use the reference motion as a training prior. So we do this by training a single policy across two tasks that share a common goal-conditioned observation space. So the first task is a reference-guided imitation task that uses dense motion tracking rewards. The second is a goal-conditioned generalization task that uses sparse task rewards. Please note that for both of these tasks, no target pose or phase variable from the reference is given as input. To demonstrate the effectiveness of our method, we use a box-based parkour setup where the robot has to perform 3 motions: walk, climb, walk, jump, and climb down. For more implementation details, please scan the QR code for the project website or come by the poster session. For now, we'll go to the results. And so for the results, we start by essentially evaluating how generalizable the learned policies are to initial conditions. And for this, we start with the walk, climb motion. So the first top row here that you see, this is the reference motion and the nominal condition, where the pink box demonstrates or depicts the nominal starting position. In the second row, we have the off-nominal configurations. And here, as you can see, the robot adjusts its climb-up strategy by either climbing up directly or walking, then climbing up. In the second video, we'll now move on to walk, jump. There it goes. And here again, the first row is the reference and nominal configuration. And in the second row, again, this is the off-nominal configuration. And here, once again, we'll see the robot's robustness to different initial conditions. Here, it either directly jumps up or walks, then jumps up, depending on the initial configuration. Lastly, we'll move on to climb down. And here, I want to essentially have your attention be on the bottom right video over here. And here, what we'll see is that when the robot is too close to the edge, it jumps backwards, then uses its foot to scooch forward before climbing down. And so next, we move on to demonstrate that the learned skills can actually be composed to solve long horizon parkour scenarios, both in hardware and in other simulation environments. More specifically, over here on the leftmost video, you can see a long horizon task in hardware. The rightmost video shows it in Majoko. Note that these policies were trained in Isaac Lab. And for this, we see that using a rule-based state machine, the robot can complete various sequences. So finally, the lesson that we want to demonstrate is that the proposed framework can be extended to more complex scenarios with minimal modification. And so for this, in order to demonstrate this, we train a single multi-skill policy with perception using one hot skill embedding and elevation map as input. And the results are on the screen. Awesome. And so with that, I'd like to thank you all for your attention. If you have any more questions, please scan the project website or come by the poster. Thank you.
For the next paper, unfortunately, there's no author here to present it in person, but we will watch the recorded, narrated video together. Yeah. Please play the video.
Hello, everyone. I'm Won Dong-sun, and I'm sorry I can't participate in the RSS event in person, but my presentation will be delivered via video. Imagine a humanoid walking over stairs, a wide gap, and a pile of rubble, using nothing but raw pixels from a single camera with no map and no special sensors. Why is this hard? Humanoids are inherently unstable. A centimeter of perception error can mean a fall. Two problems block deployment. First, the sim to real perception gap. Simulated depth is clean, but real stereo depth is full of holes and distance-dependent noise. And training with naive Gaussian noise collapses to 43% success. Second, conflicting objectives. One value function can't fit stairs, gaps, and rough terrain at once. So prior work trains separate specialist policies and distills them, which is expensive. Our framework has two stages. Stage 1 trains a privileged teacher from clean height scans with reinforcement learning. The key idea is that instead of one critic, we use 3 critics and 3 discriminators, 1 pair for each terrain family, stairs and platforms, gaps, and rough terrain, each with its own rewards and motion priors. Stage 2 distills that teacher into a depth-only student that runs on raw images. The bridge between the 2 stages, the thing that makes it actually transfer, is realistic depth augmentation. This is the core of robust transfer. We render left and right views and pass them through an 8-operator pipeline that reproduces how real stereo cameras fail. Fusion creates the characteristic holes. Then convolvulation, distance-dependent and structured Perlin noise, scale and calibration randomization, dead pixel masking, and clip-in. The encoder is trained to be invariant to all of it, with a denoising loss that aligns clean and noisy features, and a KL regularizer that prevents collapse. The payoff is that success under realistic noise jumps from 43% to 98.9%, with almost no extra power. Back to the multi-critic design. Each terrain needs different behavior. Crossing a gap rewards momentum, while stairs reward precise, flat foot placement. Dedicated critics and discriminators let one unified policy master all of them, with no separate specialists. And it works. The TSNE shows the depth encoder cleanly separating all 6 terrain types, even under sensor noise, giving the policy the right features for each situation. On real hardware, the policy runs entirely on board at 50 Hz with 0 fine-tuning and reaches 97.8% success across outdoor stairs, platforms, 30-plus step staircases, and wide gaps. To test generality, we deployed the exact same pipeline on a Unitree G1, a different body and a different camera, and it climbed stairs, 0 shot. That tells us the encoder learns transferable geometry, not sensor-specific tricks. In short, realistic depth augmentation plus multi-critic learning give robust, depth-only humanoid locomotion across extreme and fine-grained terrains. The main open problem is stair descent, where gravity amplifies errors and the foothold is occluded by the step edge. Code and videos are on our project page. Thank you, and I'm happy to take questions.
Let's thank our speaker remotely. And the 10th talk will be Mind Your Steps, a general learning framework for accurate humanoid foothold tracking. The presenter will be Alessandro.
Hello everyone, I am Alessandro Montenegro from Politecnico di Milano, and today I am going to present our work, Mind Your Steps, a general learning framework for accurate humanoid foothold tracking. So our goal is to achieve accurate humanoid locomotion via model-free reinforcement learning for complex terrains, and you can achieve this via velocity-based policies, but you have not explicit control on foot placement. So in order to have robust locomotion for complex terrains, you may rely on additional components. So you may go for foothold-based policies, directly tracking this problem, but you may need to rely on hard-to-estimate information in a real-world deployment, such as binary contact flags or the target expressed in the root frame, so required for precise localization. So we propose to slightly change the paradigm, and so to let the policy to see as goal the desired position and the orientation for both feet, but in the stance foot frame. So actually, for each gate phase, the policy is actually seeing constant targets. Indeed, for what concerns the stance foot, it is seeing 0 position offset and an identity orientation offset. Instead, for what concerns the swing foot, it is seeing, of course, a constant position offset with respect to the stance foot, and of course, constant orientation offset with respect to the same. And so in training, what we're using is a procedural goal sampler that at the beginning of each episode is actually sampling 2 heading directions, one for the movement and one for the feet orientation, so to generalize across many foot placements. And then at each gate switch, what we're doing is that we are just sampling offset with respect to these 2 directions, and of course a 3-dimensional position offset with respect to the current stance foot. At the end of the day, what we have is a general purpose low-level policy that is just able to track accurately footholds. And so depending on your preferred downstream task, you can equip a high-level planner with this policy in order to do whatever you want. So let us compare against the velocity tracking policies, in particular with this simple task of flat navigation for reaching a goal. With a comparable high-level planner, our policy seems actually to be faster and also robust. But actually, the most important experiment against the velocity tracking policy is this one, where actually the accuracy of foot placement is particularly important in order to achieve the goal, and our design is actually allowing this by design. And moreover, since our policy is actually able to track 3-dimensional footholds, it can generalize the locomotion across different terrains with complex obstacles such as stairs, ramps, or also cluttered environment, provided that you are using a specific high-level planner. For what concerns the real world, what we are using is a T1 and a G1. For instance, in this case, we have the flat navigation for the T1. We used a high-level planner that is leveraging the onboard camera in order to extract from the ground the manually placed foothold targets, and then, of course, using the kinematic of the robots, we are feeding the low-level policy with a suitable target for the policy itself. For what concerns the G1, we used yet another high-level planner that is localization-based, so it is not yet leveraging the onboard LiDAR, but as you can see, the robot can actually traverse this complex environment made of pillars of different heights without problems and with zero-shot deployment, and also it is robust with respect to foot misplacement. So it's all from my side. Thanks for watching and for listening, and I wait you at the poster.
The next paper will be PRIME, physically consistent robotic inertial and motion estimation for lagged and humanoid robots. The presenter will be Xiaobin Xiong.
Hello, my name is Xiaobin Xiong from the Shanghai Innovation Institute. I'm here to present our paper PRIME. It can jointly estimate robot motion, contact interactions, and inertia properties using an optimization with contact dynamics. And then we validate it on both quadrupedal and humanoid robots. So over the past years, the robot capabilities have evolved dramatically, from whole body control to general purpose manipulation policies. At the same time, robots are equipped with increasingly rich sensing, such as vision, force, and tactile sensing. Yet those sensor measurements are often fragmented and do not directly provide a unified understanding of the underlying physics. This motivates our question. Can we jointly recover motion, contact, and inertia from standard robot sensing? Here is the problem formulation. Given a set of sensor measurements, we formulate an MAP to optimize the distribution of Z that contains the robot trajectory x, its inertia theta, and the contact forces lambda. The optimized z thus provides the joint estimates of all variables. We propose joint estimation instead of sequential estimation is that all variables are coupled by physics. Robot dynamics describes how actuated motion evolves under inertia properties, and the contact dynamics describe robot interaction with the environment under constraints such as non-penetration, friction, and complementarity. Those constraints naturally connect the motion, inertia, and contact, allowing information to propagate across them. In our MAP, the coupling is encoded as contact dynamics factor together with the measurement and the prior factors. One main challenge of solving this MAP efficiently using gradient-based methods is that contact dynamics are not differentiable. To resolve this issue, we leverage a smooth surrogate for the contact dynamics. Strict complementarity is physically accurate. Okay, it's stuck somehow. Okay, strict complementarity is physically accurate, but non-smooth. But they are non-smooth and difficult to optimize, right? We all experienced that. So we therefore leverage a smooth log barrier version, which provides well-defined gradients and preserves the behavior of rigid contact at the same time. We evaluated prime on both quadrupedal and humanoid robots. Despite their very different morphologies and dynamics, the same estimation accurately recovers motion, inertia, and contact using standard robot sensing. Next, I will show some quantitative results. Here we attach a weight plate to the belly of the unitary go-to robot. Without any prior knowledge of the plate, prime accurately IDs the new inertia along with the motion and contact. As we show in the table here, it successfully recovers both the added mass and the shifted central mass due to the weight plate. Finally, inertia ID leads to better contact and force estimation, more so if you do it jointly, which is the main point we show here. Using the first plate measurements as ground truth for comparison, prime achieves a lower estimation error on the contact forces when the inertia parameters are jointly identified. This illustrates the key idea of prime. By jointly estimating motion, inertia, and contact, each component improves the others through the shared underlying contact dynamics. So, prime provides a unified optimization for jointly estimating robot motion, inertia, and contact from the standard sensing. Joint estimation leads to better robot models and states for model-based planning and control. Additionally, it provides richer data with higher quality for downstream machine learning tasks. Looking forward, we plan to extend this method to local manipulation and leverage physics-aware data to support future physical AI and foundation models. Thanks. See you in the poster session.
The next presentation will be Humanoids, hierarchical word frame and effector tracking for long horizon humanoid local manipulation. The presenter will be Zhanxiang Cao.
Okay. Hello, everyone. We present Humanoids for word frame and effector tracking during humanoid local manipulation. And effector tracking during humanoid local manipulation has two main challenges. First, walking causes base drift and couples upper and lower body motion. Most existing methods use body-centric commands, so base error becomes hand tracking error in the word frame. Second, distant target may lie outside the robot's reach. The robot must then move its base and reshape its workspace. Our method has two stages. In stage one, we train a whole body tracker. It takes base velocity, body height, and end effector poses, and output joint target. A pre-trained kinematic manifold prior or KMP gives a valid upper body reference. The policy only learns a small residual correction. This makes training easier while keeping the motion flexible. We also sample more reachable hand targets during training. A history encoder summarizes recent motion. A state estimator predicts base velocity and cleaner end effector poses. Finally, the upper body follows the desired end effector poses with the KMP reference, while the lower body controls locomotion. In stage two, we freeze the tracker and train the word frame commander. It receives the hand target and the robot's global pose, then commands
the base, body height, hand pose, and waist motion. The robot first walks toward a distant target, then uses its torso and arm for accurate tracking. A curriculum gradually increases the target distance. We first test our low-level tracker on real Unitree G1. The robot moves smoothly from standing to a deep squat while keeping its upper body on the target. It also walks with the right arm held high, and while the hand chases a circle. This result shows stable tracking despite large body motions. Next, we test 5 word frame passes in simulation: circle, heart, rectangle, spiral, and star. However, preserve each shape while the ablated methods show larger error and visible distortion. The real robot square and the circle result on the right show the tracking performance. Here is a full simulation. The robot first walks to the target. The left view shows its base pass from above. The right view shows the hand chasing a circle at a fixed point in the world. The next sequences show the other 4 passes: rectangle, heart, spiral, and the star. The robot keeps adjusting its base while checking each pass in the word frame. Even at sharp corners and quick direction changes, it stays balanced and preserves the overall shape. Okay, thank you for your attention.
Last but not least, the presentation will be Omni Extreme, breaking the generality barrier in high dynamic humanoid control. The presenter will be Siyuan Huang.
No, Shaohang Zhu. Shaohang Zhu.
Okay, the presenter will be Shaohang Zhu.
Okay. Hello, everyone. I will introduce our work on Extreme. This work is joint effort between Big AI and Unitree Robotics. Okay, let's begin. The motivation of this work is to make humanoid robots to have human-like motion intelligence. In character animation, humanoid characters already come from a huge variety of full body motion, like flips. Wait, sorry, this screen is not open. This screen.
You can wait over there. Hey, you can wait over there.
Sorry. Humanoid characters already come from a huge variety of full body motivation, like could we restart? Sorry. All right, I will continue. And for real world, I just have one here. The motivation is that the robot can overfit very well, and for general policy, the robot's ability decrease as the skill increases. So we call this problem the generality barrier, and we want to build we want to tackle the generality barrier by tackle 2 bottlenecks. First is learning bottleneck, and the second is physical bottleneck. Learning bottleneck is because the recent work uses the simple training set, which using MLP and direct RL, and need more impressive representation. And the second is that physical bottleneck. The naive view is that this always using the domain randomization and sensor noise. And there are another very critical since it's using acceleration with delay and sorry. And to do this, we building an extreme motion set and try to figure out the question: can one policy handling diverse challenging motion while maintaining scaling to diverse skills? And I will talking about our method. Our philosophy is decoupling the philosophy is decoupling the pre-train stage and the post-train stage. The pre-train stage is try to study better, and if the learning is weak, so the policy may fail even in simulation. So we train many experts and doing distillation using a full matching model and to train a unified model. And the post-train stage, we fit in a full matching model and using a residual network with actuation constraint. And here are the real-world results. And from the table, we could see that our policy achieves consistently high success rate and across diverse scale. And here are the real-world results. And the first video is about to alternating pistol squats with consecutive squat and kick. And the second video is 5 consecutive Weber flip, which showing the robot the policy have strong robustness, and the below two showing 2 long breaking dance with rapid contact switch, and the second one is doing backhand sprint while dancing. And one's worth mentioning is that the policy is fully on board, powered by TensorRT and C++ development on Unity robot, and this showing that full matching policy is capable real-time deploy. And thank you very much for listening.
Okay, thank you. We invite all the authors to come to the stage to answer the questions. Yeah, for the audience, if you have questions, please line up in front of the standing microphones or just wave your hand to our volunteers. Okay, for audience, if you have a question, could you please wave your hand?
Okay. I can't really see it. If there's any
Yeah,
question.
can you raise your hand?
Okay, there's one question. Yep, go ahead.
Hello, I have a question for PHP. Your work is very awesome, and I have a question. I have do motion matching recently, and I have a question. Why your work use motion matching to generate data, and not use motion matching and tracker to make a generalized policy? Sorry. I mean, why we not use motion matching to take the role of motion tracker or motion generator?
Thanks for the question. Do you mean why not using motion tracking during the inference time? Is that the question?
Yes.
Yeah, so thanks for the question. That's a good question. So because when motion tracking needs some privileged information, such as like the body velocity, body global position, so which is not available during the deployment time. That's why we only use it for data generation instead of during the deployment.
Okay, and motion matching is infer FPS is okay for real time.
Yeah, it's definitely okay for real time, because in the all the video game, it's like they are using motion matching and they can achieve like 60 FPS or higher. So yeah.
Okay, thank you.
Thank you.
Okay, we have the next audience for question. Yeah, please. The gentleman. Yeah.
Yeah. Hi. Also question about PHP, please. Do you have any answer why you're not using elevation maps and you use depth camera? And if you will answer me because of odometry, please tell me why we don't want to fix, like to make odometry precise enough to make reliable elevation maps for sampling. Thank you.
Thank you for the question. So why do we use depth camera instead of the elevation map? I think both should work. So it's just like a design choice. We choose, we are familiar with the depth camera, so we just use it. But depth elevation height map definitely works as long as it can have the they can see all the obstacle and the ground. That would be work. It's just like a design choice. Yeah. And for the second question, could you repeat again? Sorry.
No, you answered. Thank you.
Thank you.
Okay, thank you. Next question. I hope it's for another paper.
Hi, so this is addressed to the Husky paper. The skateboarding simulation, I saw that in the real world there were like issues where you had to have safety. Is that because of a mismatch between the actual skateboarding model, or is it just an issue with the humanoid learning? And can we expect like in the future to have humanoids that do skiing and snowboarding, or is that a more difficult modeling problem to solve?
Thank you for the question. So you mean where is, from my understanding, so your question is where is the largest sim to real gap is? So I think the main sim to real gap is the skateboard itself. So in our system modeling, we just abstract the skateboard model into a simplified but working model. But it can substitute the real world skateboard. It have very complex mechanical structure. And I think this is the main sim to real gap. And for other sim to real gap, I think it's we don't have enough money or robot to perform so dangerous experiments and explore how can we achieve better skateboarding performance. So if you have more questions, welcome to our poster session. Thank you.
Hello. Okay, we will have our last question. Yeah, please.
Okay, thank you. May I have a question for the Psi0, the fundamental model? Yeah, hello. Thank you for your awesome work and the open source model and checkpoint. But I have just one question. You know, in the if I'm right, your upper body and the lower body are controlled decoupled. The lower body is only the command of velocity. So in the real world, when you collect data, how do you get the velocity of the real world robot? Do you only just use the odometry, or you use any other sources or algorithm?
Yeah, thank you for your question. So in reality, we have two pipelines. The first pipeline is just using a Vision Pro, and we need another person to use the unitary controller, and the controller would control the velocity commands. And the other pipeline is a person would weld the Pico tracker, and we would extract the velocity and the orientation command directly from the Pico waist tracker, and that will be sent into the RL decoupled policy. Yeah.
Okay. Okay, thank you.
Okay, thank you. Let's thank our presenters again, and also the co-chair, and also organizers. Yeah, this concludes this session. Yeah, I hope you will enjoy your stay in this beautiful city, Sydney. Okay, this concludes this session.
The music's mysterious, bringing together you and me.